Alright, so here's kind of the way my thinking is. I got a carbonyl. This is a Lewis acid. This thing is going to be attracted to that, and so if my electrons come into here, it's going to kick that out. I'm going to end up as an O minus, and then it's going to pick up this hydrogen, and I've just made my hemiacetal. Wow, I'm done. Does that make sense? Is it easier to understand than just, I take a ketone and an alcohol, and I make this thing called the hemiacetal? But we know why it's a hemi, because it's just a half acetal. And again, say that slowly. A full acetal will have another one there. And so we can do this reaction one more time. All right, yes? A full acetal will have, see how this is an ether right here? It will have another group. It'll have this group right up there. All right? Fun stuff. Yeah, this thing always worries me because it is kind of hard. Carbonyl, but these additions, this is what we're saying. It's a polarized double bond such that the carbon carries a partial positive charge and the oxygen carries a partial negative. So being electron poor, a strong nucleophilic reagent will attack that electron poor site. And then we work it up at the very end. So again, here's my aldehyde, here's my alcohol, this is my hemiacetal. Okay? Now, that said, if I come in and I do this again, here's my hemiacetal, and I bring in another alcohol, I get the full acetal right here. So we just add another group on, twice. Yes? Ultimately, yes, that is how that works. Yeah. So the way this really goes is this gets protonated and starts to pool on here. So the electrons right here push down and kick that out, and it makes this a carbonyl again, and then the new alcohol comes in here and kicks that out again. But that's not the coolest part. Hopefully, as we look down here, any questions on that? I'm going to try to give you, I'm hoping that I'm going to give you a way to even remember this a little bit better. There is your, and of course, if you do it with an aldehyde, you retain the aldehyde portion. If you do it with a ketone, you retain the ketone portion. Now, for the sake of, again, to prepare you for the unknown, I might write down in my book that the acetal really came from the acetaldehyde. You see how that name comes from? The ketal comes from the ketone, and we don't use that anymore, at least not in this book. For me, if I'm wanting to be, the top puppy, I write down the possibility of ketal from a ketone, just in case the ACS exam hasn't caught up with the book. I just keep all these little tiny things in my mind, and it's not something I worry about here now, but on that weekend when I'm studying for it, it's something that I would bring out after I studied everything else and says, I'm good. Oh, let's look at these things that Ty said could potentially trip us up and separate us out. Because this class, I'm going to tell you, Ezra, just off the top of your head, how many 90s do we have in this class? 16. In any other class, there's usually 4 or 5. 4 or 5. We have 16s. My bet is if you keep this up, we are going to rank in the high 80th percentile, and the other classes will be down in the 60th to 70th. We ought to just kick the trash out of them. And let's be really clear, I'm competitive. I do want you to just be the best of it, because that means more of everybody in here gets into nursing. May not be the first semester, but the second semester. That still stands. You can't ignore a standardized exam that was written by other people, not me. I mean, I could write an exam you could all get 100 on, and then, they're going to say, yeah, but you wrote that. So this is the American Chemical Society writes it. I don't ever get to see it, and you don't ever get to see it. This is how you rate in the nation. So to go in there with a good grade at SUU is meaningless, but to go in there with a high national nationally standard ranking. And especially if you can get all of them, you're in the 100 percentile. You can't ignore that. You know, you just can't ignore that. So it's an awesome thing. This is the most 90s I've ever had. Yes?
On that top reaction, so we're going from acetaldehyde to acetal because we have the acid catalyst. Without that catalyst, we would just go to the acetal.
Yeah, without that catalyst, it really, well, you really need the acid catalyst to get it to go to the hemi. Without the acid catalyst, the two just sit in solution in hydrogen bond. So that acid catalyst protonates this and makes this be able to come in and attack it right off the bat and get rid of it.
So it increases the acidity of that carbon.
There you go. That's good. Yes, that's exactly right. I'm going to convince you to be an organic chemist, do novel drug design and delivery. I mean, it's a blast. All right, good answer. Yes.
So, what is the determining factor that
Makes all this go.
no, what distinguishes heavy acetal
Ah,
from,
so note how I got the two ether groups here.
well, no, I mean just like, you said the acid catalyst will ultimately make that a heavy acetal, so why is it making it whole?
Because we're using extra of the alcohol. So, I don't know if you talked about Le Chatelier's principle in 1110. That's really what it is. We're loading up this other side of the equation with an excess of alcohol. So, truth in lending here. If I'm going to do this reaction, I'm going to take my aldehyde and I'm going to take one equivalent of that. And you know what I'm going to drop it into for my solvent? The alcohol. I may have 10 times the alcohol that I need, but it's my solvent. It will dissolve both of them because they will hydrogen bond. So my solvent is also my reactant, and that then is Le Chatelier's principle of an excess on one side, driving this all the way over to the other side. And so here, I create a little tiny flask as I'm heating this, and the steam comes off. I get it to condense the water, and the water come over here and just get separated out. So then I hit it from both sides. So that's the difference, is the excess of the alcohol. If I just use one equivalent of alcohol, I'll stop at the hemi. If I use two or more, I go all the way to the full-blown acetal. Now, this looks weird, and I know it looks weird. Because it looks weird, so you have, these are all just the same thing, showing you it's a variety of different looks, so that you get used to different looks. The hemi and the acetal. But I want to show you my favorite slide. Give me my favorite slide. Where's this? No. There we go, right here. Here's my favorite slide. You can do, so you can actually use this as a protecting group. So sometimes in reactions, this is too much of a Lewis acid. So if you turn it into an ether, it becomes non-reactive. And so instead of using two different alcohols, they put the same alcohols on the same molecule, and the product is remarkable. I call this the Bartman reaction. I don't know if you still look at The Simpsons. To me, when I first saw that, that looks just like him. So that's how I remember this. It's the Simpson reaction. I call it the Bartman. And you're free to call it the Bartman too. Because this gives me all the different varieties that I can have. You know, if I look at these things, we kind of get stuck in a general form. But so here on the practice ones, I'm giving you, hey, here I'm giving you a propylaldehyde, propanal, and a methyl alcohol. This one is made from 1, 2, 3. Okay, so this is going to be made from 1, 2, 3 pentanone. It's going to be the ketone 3-pentanone. Okay. And ethanol. But in each case, we're bringing in the two alcohols. So I thought, really, what we use this for in research, there is a 1, 2, 3, 4. So this is butanal. Okay. So draw the condensed structural formula of the acetal form by adding this to butanal. Boy, did I give you? Oh, okay, there you go. But also, I would say, let's do it backwards. Isn't that right, my TA? We're going to say, not only show me the aldehyde and the alcohol that comes from this. That is something that I think an ACS exam would try to separate you with. But if you you can get to here, you know that these are the alcohols, so you wipe out the alcohols and you just put the, put that aldehyde right there. That's the butanal. So think of these by going forwards and backwards. Okay? Here they're giving you the name, methanol to butanal, and then say, okay, now I have this, what did it come from? Because synthesis gets to be important, how to make these. And then might say, how would you synthesize this acetal? Well, I know to move this, so I'm going to have my methanol and my butanal. Does that make sense? Because synthesis is supposed to be a little bit harder than the reaction. To me, it's the same. I just go backwards. And if you get in the habit of going backwards, it'll be the same. Yes?
So this one would have come from like 2 methanols, right? Exactly.
Yes, it would come from 2 methanols. Yep, absolutely. So to even be trickier to drive this home, to get a full acetal, I have to have 2 alcohols. So what would this look like? And sometimes students are like, oh my gosh, I don't know. I mean, I'm used to putting 2 methanols on there, but these 2, the methanols are connected. I want you to see that just because this is what I really think that an ACS would do to you, because this is the most popular form of this acetal, is this one right here. And all they did, there's still 2 methanols, they were just connected together. So no matter how the alcohols are, 2 alcohols give me a full ketal, or acetal, excuse me, it's an acetal. This is a ketal because it came from a ketone, but it is an acetal, yes.
What is the lines connecting the oxygens?
Well, these things right here is just a bond. So this is a CH2CH2OH. So what we did here is we took Prestone antifreeze. Do you remember when you had to memorize this ethylene glycol? Ethylene glycol and butanal. So this is just a diol instead of an alcohol. It's now a diol. To make a ketal, what we're saying here is for you to make the connection that in order to make a ketal, I have to add 2 alcohols. But what if I attach the 2 alcohols together? Then I make something totally different. But it's still exactly the same reaction, same mechanism, it still occurs the same. It just looks weird. And this is the #1 use of this outside of nursing. It is a chemical use. Nursing, this is all about closing the sugars and opening the sugars. It's what it really is in terms of how you eat it and how you go. But that, I think, and so there we go. You see, here we are with our aldehyde, and here's my alcohol. See? So we're back to where we started. This can reach around here, just like I have, 1, 2, 3, 4, 5, 6. I can reach around and grab it and form a 6-membered ring, which, by the way, as we remember, is the most stable. That chair, the 6-membered ring is the most stable ring. It's more stable than a 5, a lot more stable than a 4, which is a box, and a lot more stable than 3, which is a triangle. So this is why your body uses it. Your sugars are in mostly 6-membered rings in this hemiketal form. Pretty cool. And you'll see that over and over and over again. When we get to glycogen, hopefully I'll remember to stop and say, hey, what is that called? And it's a hemiketal. And learn to find them. And there you go. The hemiketal of glucose. But again, Lewis acid, Lewis base, it can reach around and pick it up. But here's my ether part from the alcohol. Here's my alcohol. It's just a long alcohol is connected to itself. And then it's a heme. So by showing you a variety of these different looks, it makes this sugar hopefully not that odd to look at. Because that's what exists in your body. It opens up and closes over and over and over. And we'll talk about it. We'll come back to this reaction in the sugar chapter after we've taken the organic ACS exam. So there you have carbohydrate. And this is just drawing it out for you. So if you wanted to see how this was, Namely, what I do is I come over here and I just drop this 90 degrees so that I know that if this was down and this was up and this was down, then as I dropped it, it would be down, up, down. See? Down, up, down. And then I could drop. I don't think you ever have to do that, but when I look at these things from a medicinal chemistry standpoint, that's how I do it. I just drop it down and then I know to take this, once it's down, and connect it together into that Hemi, and I know what that looks like. Because it is on the backbone of your DNA, and your DNA is what makes you you. It is what your foodstuffs are. It is at gates and pumps and channels, these sugars. It is what marks the passage of time in terms of blood clotting and a variety of things. Sugar is in aging. Sugar is one of the most important things, but nowadays we only look at sugar as I gain weight and it gives me diabetes. Here's something just to predict down the road. Sugar is everywhere. It's on all of your tissues. It's what blood typing is all about. Your sugars. It's your sugars that makes you be A positive, O negative, or O. Sugars are everywhere. I believe that the next real great discovery in medicine, besides coming from genetics, will probably come from sugars. Because a long time ago when I first started this, you see, biochemistry in medicine as we know it today is really my age. It's only 60 years old. It was first discovered in the mid-50s. And then about the 80s and 90s, we got to where we could understand this Lewis acid, Lewis base thing. And so we could build things to really solve medical diseases. But I remember starting out when I was first teaching it going, you know, we have this DNA binding site on almost every reaction. Well, now we realize that it's ATP activates things and GTP activates things or shut things down. But there's more, there's sugar binding sites on all of these things too. What is the purpose of that? And I believe we can have some medical discoveries from that. But that's for younger people. So here is, this is kind of fun, 1, 2, 3, 4, 5. So this is going to be sucrose, this is going to be table sugar. Glucose and fructose put together. This is table sugar, how it goes into your body. Now the trick is, from here, could you find the hemiacetal? Or a full-blown acetal? Or a ketal? Actually, they're all going to be acetal. So here is where we had the OH earlier, right? Let's go back to this thing. This was the OH, right here. And so it was a hemi, correct? But now if we took this OH and bound it to another sugar, then we have the ether here and the ether here. And look, this was the aldehyde that it came from. This was the carbonyl, right? This was the aldehyde, but now it's connected to another sugar. So this is a full-blown acetal right here. And so here's another one here. But this is a carbon and this is a carbon, so this came from a ketone. This is a full-blown ketal. So when this breaks apart in your stomach, you would have this glucose, and then this is fructose, the 5-membered ring and the 6-membered ring thing. Because eventually we're going to break those down like that and see where they go into glycolysis in the citric acid cycle. And that will probably be the hardest chapter, but because we keep coming back to that, it makes the rest of the year easier to understand. We just keep coming back to the same things. So I think that's probably the hardest thing to do, is to find that in a sugar, or to find the ketal, the acetal, anyway. All right, so that's the chapter summary. That's it. That's in the chapter. So tomorrow we will then start the carboxylic acid chapter. You know what we're going to do? We're going to name it, but guess what? Carboxylic acid is the highest priority group. We're done. Wait, this is the end of organic, isn't it? We have one more week of organic. And that's going to be next week. And so then the following Monday we have our test. So we're going to have probably some extra days to study, which is good, and I like that. But I'll have to, you know, if we take a day off, I have to give you a homework assignment to study and come to recitation, because my colleague thinks that's offensive that we took a day off to do it. But the nice thing is, great day. See you later. See you